Hi again, everyone. Unexpectedly, I became the chair of the next session. Our next speaker will be talking about bridging the digital divide, a tailored digital maturity model for SME transformation. Right? No? Oh, sorry. Yes, okay, yes, I'm sorry, apologies. That will happen later in the day today. Yep. So right now, we will be listening about some applications of Markov chains for cyber-physical systems analysis, and our presenter is Volodymyr Skobelev. Okay.
Okay. The problem, we will consider it, is reflected in the slide. Next slide, please. I will explain why this problem has been selected. You know that at present, cyber-physical systems are used widely all over the world. What is a cyber-physical system? Cyber-physical system consists of two subsystems. Cyber system that consists of computers, controllers, and so on, and physical process or processes. Physical processes supply cyber part through sensors by data. Based on this data, cyber part select the mode for physical process. So such mixed, continuous, and discrete dynamics is back. Real cyber-physical systems has two properties. Firstly, they are very complex, and the second, that there is high diversity in their structure. These two reasons led to the fact that the single approach for analysis dynamics of physical behavior is made only via mathematical models. A test model checking approach is a single approach then that can be explored in reality. Maybe the most known model for CPS is the so-called hybrid automata, determined or non-determined. What is a hybrid automata? It is directed graph in which vertices present physical processes and arcs present discrete transitions from one mode to another. Different problems need different types of models. There are some problems for analysis of cyber-physical dynamics, behavior analysis that can be solved only via stochastic models. Among these problems, maybe the most important is the so-called functional safety. It includes at least three components. First, reliability. Second, security. The third is parameters analysis. It is clear that these problems can be successfully solved only via stochastic models. So, stochastic hybrid automata has appeared. They can be characterized as follows. Probabilities are associated with arcs, and resetting of continuous variables is due to the given continuous distributions. It had happened so that most of the problems are algorithmically unsolved for such general models. Besides, when you solve some specific problem, only a little part of information connected with cyber physical system is used. This fact was the reason to simplify the models. Then probabilistic hybrid automata has appeared. The processes are deterministic and probabilities are only on the axis. Such models can be applied for very few cyber-physical systems. So mass efforts have been directed to create high-level models of cyber-physical systems. What are high-level models? These are the ones that use a very few information about cyber-physical system structure or doesn't use this information at all. Among such models are the ones based on Markov processes. The simplest and maybe most widely explored subclass of this class are the ones based on Markov chains. So I will consider three types of Markov chain models that are applied or can be applied for cyber-physical systems behavior analysis. They are the ones based on iterative random function families on the given set of state, discrete time finite Markov chains, and continuous time finite Markov chains. Next slide, please. So let's consider the first class. Models based on ERF families are defined by the recurrence relations. A test, this is analytical in common sense presentation of dynamical systems. How it can be done? First of all, we get some functions family from S to S, where parameter theta is element of some set theta. we are given some probability distribution mu on the set theta. Using this data, we can construct recurrence relation of this form S, the state S at n+1 instant is function f with index theta n+1 applied to state at the nth instant. I will consider application of this model to specific problem, a linear model for planning of production system. And I like to mention that these models present Markov chains, infinite or finite. It is evident that Markov chain is finite if and only if the set S is finite. Next slide, please. So let's consider the following linear model. Do you see it, or I must read the formula? Here, A sub n is DD matrix, B and C with index n are D1 vectors, triples AN, BN, CN are independent and identically defined. Xn is independent from the triple AN, BN, CN. What is interpretation of this model? Xn is store inventory amount at the day n beginning. AN is store technological matrix. BN is inventory amount ordered and delivered at beginning of the day n. CN is the amount of inventory sold during day n. So we have elaborated planning strategy in such form. In practice, such strategy is planned for finite horizon, saying for L days. When this model is elaborated, first of all, we have to prove its correction. It is evident that Bn and Cn must be vectors with non-negative components, so Xn for all days n. Then each real planning strategy must be bounded. So we must check if this condition is satisfied. It is very simple. To satisfy this condition, we must check that IN, BN, CN, and XN are bounded by norm. Besides, we must prove that this stochastic model has the single stationary distribution. It means this distribution must be independent from the initial value of store amount. It can be checked easily too. So we get some adequate, as we think, planning strategy. But in reality, each physical, real cyber-physical systems is acting in environment with some disturbances. These disturbances can have big influence on real situation. So we must correct our model. How can we do it? Imagine that x sub 0, x sub k is real inventory amount. And x0, xk are planned inventory amounts. Of course, some adaptive mechanism must be developed. What is this mechanism? Before beginning of each day, we estimate the difference of norms between real and expected inventory amounts. It is supposed that some threshold delta is given. If this difference do not exceed delta, then we act for the next day as it was planned. But if this difference is greater than delta, we must change our planned strategy for all the tail. So we change it, and from this point, new planned strategy is applied. It's all that I have to tell about this model. Next slide, please. The second class of models are discrete time finite Markov chains. I will say some words about discrete Markov chains. They are defined on the finite set S sub 1, S sub n. It is supposed that we are given with stochastic matrix. What is it, stochastic matrix? It's a matrix with non-negative values, and sum of elements along each row is the unit. So when we have some initial probability distribution of states, we can recurrently compute distributions at each instant of time. Moreover, we can compute stationary probability distribution as solution of the equation. Some words must be said. Я скажу когда. Computing uses formula is not difficult when matrix P is not big, but its complexity arises rapidly with growth of the size of the matrix. So bounded analysis can be applied. This analysis is based on searching for counterexamples. What we do, we build level by level decision Markov tree. And if probabilities on such some level are greater than the given threshold, we say that some critical states can be achieved, and we give you the counter example. If we built our tree for the given depth and the threshold was not exceeded, then we say that everything is all right. The critical states are not achieved. Next slide, please. I will consider the application of discrete time finite Markov chains models for solving of some problems. The first problem is the following. We want to model the dynamics of CPS that can function in the presence of faults. How this can be done? As usually in technical diagnostics, it has, first of all, we define some single fault sets. Then we define multiple fault set as set of subsets of single faults. Maybe not all, but multiple faults are subsets of single faults. Then we create analyzed state set. We add to this set the fault-free cyber-physical system. Then we define critical fault set as the set of all maximal elements of the analyzed set. The simple example, let's consider the net consisting of 3 identical computers pairwise connected. Of course, these computers can be faulted, so we have the set of single faults. The single computer is faulty, then the set of multiple faults, 2 computers are faulty, or all 3 computers are faulty. So we have Markov chain in which states can be partitioned into sequential levels. The top level is fault-free system. The first level is the net with only 1 fault faulted computers, the next level. Two computers are full with faults, and the last level, all three computers are faults. This Markov chain, there is one more additional rule. At each instant, fault may occur only into single computer, and only single computer can be repaired. So we have such Markov chain that is completely connected, and at each vertex is a loop. It is known that such Markov chains are aperiodic and irreducible. So for them, there exists the single stationary distribution. Of course, it is preferable to analyze such Markov chain presented in parametric form, because at once we solve a class of similar problems. And moreover, we can apply some mathematical analysis. It is, we can find what we must change to improve our system. The next class of problems that can be solved with discrete Markov chains are the so-called degrading systems modeling. What is the problem? It is well known that for any real system, its functioning is degrading due time, because wear of and aging of its parts. If such cyber-physical system is left unanalyzed, then it can be out of use. So maintenance policy must be developed. For developing maintenance policy, some mathematical analysis of the associated Markov chains must be done. And it has happened interesting thing that due to appearing of cyber-physical systems, except of completely repairing systems, we must consider also partly repairable systems and non-recoverable systems at all. How can it be done? It can be done by using the structure of the graph of Markov, associated Markov chain. It is supposed that vertices are partitioned interlevels of that reflect the degradability of the system. The same condition from each level vertices are not connected between themselves, and only vertices of previous or next level can be achieved. The single vertex of the last level has only a loop. So the cyber-physical system is completely recoverable if we can reach initial vertex from any vertex except the vertex that is on the last level. Is non-recoverable if no vertex of previous level can be achieved, and partly recoverable if we can achieve previous levels for some level, and then we cannot go upstairs. Maybe the most known example of such cyber-physical system is the system applied in modern medical centers. I present you a very simple example. Let's consider chronic disease that is intended to make diagnosis and the medicines for the given patient. It consists of 4 vertices. The highest level consists the vertex that is the healthy patient. The next vertex is the first stage of chronic disease. The next is the second stage, and the last is the patient is death. So we can analyze this model in parametric form and define some preferable trajectories. Then when we analyze specific patient, we put numerical values instead of parameters and get real picture of his life cycle. And the last models are continuous. Next. Continuous time Markov chains. Давайте. Нету времени. Okay. 2 phrases. The scheme for designing such models is the same as the scheme for design of discrete time models. Only actions on each step differs. Thank you for your attention.
Thank you so much for the presentation. I think we can take one question, if that's okay. I'll pass the microphone.
Thank you very much for your presentation. My question is, your talk was dedicated to mathematical models for cyber physical systems, yeah, to assess metrics indicators of behavior of such system. Yes, my question is the following: how we can parameterize this model? I mean, if you talk about failures, about changing of states, we need to understand how which parameters, which values of parameters to go ahead and to calculate, to apply this model. Hence, parameters. I mean, for example, is a failure rate for hardware or software components, recovery rate for different components, and so on. Because usually it is a very important problem, and we understand if the parameters value will be not practical result of the models will be difficulty to apply the practice. Thank you.
Thank you for your good question. But
Can speak there.
the parameters are connected with the model, not with the problem. Instead of numerical values, we put symbols and we analyze the structure in symbolic form. For example, we consider formulas for probabilities of this or other properties. And then we use standard mathematical methods to analyze these formulas. If we can change something to make our structure better, we do this. If not, we don't do it. Of course, we must use numerical values after to do it. But we make our analysis in symbolic form. But you, of course, you're right that for any specific problems, to select parameters for model is very difficult problem. I do not discuss this problem. This problem must be solved by specialists.
Mm-hmm.
This matrix which we see now is a typical matrix for Markov models, yes?
Yes.
But for example, if you talk about software components, rate of failure rate will not be constant. Will be changing, taking into account operation process. For hardware, it will be another. Hence, if you talk about cyber physical systems, we need to take into account real components of the system. Just my comments. Thank you very much for your answer.
Thank you for the discussion, and I suggest you take it during the coffee break or during the lunch, right? Okay, because please, we'll take it over lunch because we're limited in time and we're a little bit over time right now. Thank you so much. Applause again. And now I'm inviting to the stage Vadim Ermolayev, the one and only, with a talk that is called Grids-Based Spatial Indexing for Geometrical Data Processing. And I encourage everyone to speak closer to the microphone since we have 6 more people listening to us on Zoom, okay? If you don't mind.
Thank you very much for the introduction, Mariana. I'm just sharing the presentation and okay. If you please stop discussing, I will tell you an insight as a reward. Thank you very much. So The story is, ladies and gentlemen, that I have no relation to this paper and I have no relation to this research. Sorry for this confession. The situation with Andrii Dashkevych, who is the author, was that he was not allowed to leave the country because of the constraints of the martial law. So we found a sort of a solution that I will take the material, he will prepare the presentation, I'll try to refurbish it slightly just to put some additional effort in and present this research for him. Sorry about that. Well, but anyhow, I will do my best. So the paper is grid-based spatial indexing for geometrical data processing. The author is Andrii Dashkevych, who represents the Department of Geometrical Modeling and Computer Graphics of the National Technical University Kharkiv Polytechnical Institute. Myself, well, you know, I'm just a speaker for Andrii here. So this is, oh, come on. Yeah, this is the plan. So first, Andrii will provide you with the motivation to do this research. Then we'll do some brief analysis of the state of the art, showing you different ways to solve the problem he is researching, he is focusing on. And then we'll present the research contribution as a step forward in pushing forward the state of the art of the plethora of the methods. We'll then demonstrate how the new method developed by Andrii has been evaluated in terms of time spent for the computation and memory consumption during the computations, which will be compared to the different background methods. Finally, we'll demonstrate you the example of an application where this approach could have been applied and already tested by Andrii. So, starting with the motivation, I would be saying evident things. For example, I will be saying, following Andrii's line of thought, that most of the available data in the world today are discrete in nature. This slightly contradicts to the previous presentation, but anyhow, this is the grave truth of our life. The most data is discrete and involves or includes digital images, audio-video data, voxel geometric models, routing planning data, biomedical records, water genetic records, knowledge representations, digital triple challenge tests, data sets for machine learning models, and a lot of different stuff, which is discrete. And the volume of data, you guess what, is constantly growing. So there is a need to process these constantly growing volumes of information more and more efficiently to keep with the pace of this life. There are some generalized practical spatial-based problems which are relevant for this research. Those are search for close points and comparison of points, like for planets, for instance. Computational geometry, for example, looking for object intersections. Data classification and clustering, like in natural language processing or image processing or whatever. Location of points in a space for just finding the conference venue place. So the state of the art, And please do not blame me. I have no relationship to this analysis of the state of the art. Contains several approaches and data structures to solve or optimize spatial problems in regular, uniform, and non-uniform grids. So Andrii says that the current trend is to follow the grid-based approach. And the grids could be uniform, which is a little bit more simple, and non-uniform, which is a little bit more advanced. So the approaches are based on space subdivision using tree-based data structures, and the time complexity here is n logarithm n. Space indexing or spatial hashing, where the time complexity is linear. So the key required properties of the foreseen or the required solution of a grid-based indexing function, which has been developed in this research, are minimize the computation time, minimize memory consumption, account for the presence and account for the proportion of index collisions, which mean equal indexes for distinct grid cells, account for locality sensitivity, which is the preservation of relative distances in locale, account for index reversibility, which is the property which allows to restore the whole data set based on the index data. So these are the methods which has been analyzed as the part of the state of the art to compare with the developed approach. The categories of those methods are arithmetic-based indexing, which includes universal hashing. The properties of the universal hashing methods are that those methods are randomized, non-reversible in terms of the absence of the possibility to restore the whole data from the index structure. Those methods tend to have collisions. They're not locality sensitive, and their memory needs are linear with the growth of the grid. Spatial subdivision methods, including locality sensitive hashing or LSH as we know it, are randomized, non-reversible, tend to have collisions, locally sensitive, and need exponential memory with the growth of the data. And pivot indexing. Those are randomized, non-reversible, tend to have collisions, locality sensitive, and also need linear memory. So the aspects which we use to compare different methods in evaluations are time consumption, memory, collisions, locality sensitivity, and reversibility. So this is the part of the experimental setup. We'll take several different methods from this menu. We'll add the method developed by Andrii and compare all those based on these aspects. So what has been developed? The approach which Andrii calls regular indexing, which includes regular uniform indexing for uniform grids and regular adaptive indexing for non-uniform grids. So both approaches, both methods are reversible for both variants, which means that there is already an opportunity of those methods because they allow you to restore the whole data from the index. So the regular uniform index is built based on the formula presented here in the slide. Oops, sorry. What happened? Sorry, guys. That's what I'm doing. No. Screen is here. Third screen. Okay. Yes. Here we go. Here we go. And here we go. So again. So regular uniform indexing is done using this formula, and the regular adaptive indexing is done using that, and this addition to the regular uniform indexing is in fact accounts for the adaptation for different grid cells. So let us go and see the results of evaluation experiments. So the first experimentation has been done to evaluate how much time does it take for the new method to build the hash table. So the experimental setup is given in the screen. It's AMD Ryzen 5 4500 processor with the 64 gigabytes of DDR4 RAM. And the software part has been implemented in Python 3.12.4 plus NumPy library. So the task for this evaluation experiment was to measure hash table generation time for all cells of a two-dimensional uniform grid where the number of cells in a grid is in the range between 20 and 1000. So you may see here in this diagram that the regular uniform indexing takes the minimal possible time among all the competitors here, which is already a good indicator. Then we made memory consumption evaluation by comparing this regular uniform indexing with the methods mentioned before, with the background methods. So the key values for memory consumption evaluation were hash space size, number of filled hash table cells, and the number of hash table cells with collisions. So the task was to index all the cells of the two-dimensional grid with the t equal to 32, and the hash space size is t square, which equals to 1024 is the minimal required hash table size. We have several parameters here given in the slide. So if we look at how the parameters changed based on the changes in the number of the cells with the in the size factor, you'll see that the number of cells with collisions remains considerably low for universal hashing. This is the first group of methods in the list. The hash size table growth linearly, and the number of filled cells is also quite small. So it says that despite the growth of the size of the hash table, it remains very sparsely filled. So which says us that those methods do not really use memory efficiently. So if we go further and look at pivot indexing, the situation becomes slightly different, but still we may see that memory consumption is a little bit overestimated by pivot indexing methods. They do not really use all the available memory in an effective and efficient manner. So this is for locality sensitive hashing. The situation is a little bit better here, but if If we go following the increasing number of the field hash table cells, we'll see that finally the method based on pivot and on locality sensitive hashing will become not very effective and efficient in using memory as well. So, and this is for regular uniform indexing. So this diagram says that the curve of the field cells in fact lies on the curve of the hash table size, which means that the hash table is very efficiently used and almost all the cells in the hash table are filled. So this is the indicator of the fact that the number of that this is the optimal size of the hash table, and in terms of memory consumption, this method is the best among those compared to it. So if we compare the evaluation results, we have to say that as for time evaluation, all the evaluated methods spent linear evaluation time for building hash tables. As for the memory, the consumption evaluation, we may say that universal indexing allows defining hash space size. And hash space is underutilized because not all hash values may be obtained. It is not locally sensitive, it's not collision resistant. As for the pivot indexing, we may say that it is linear in size, locality sensitive, non-collision resistant. As for the locality sensitive hashing, the memory usage is exponential inside. You remember the shape of the curve in one of the previous slides. And the hash space is highly underutilized, especially at the very end of the game. It's locality sensitive and it's not collision resistant. For regular indexing, the experiments showed that discretization degree, T, is the only parameter for this method. And collision resistance for any value of T is good. There are no very many cells with collision for any value of T. It fully utilizes the hash space as seen in the previous slide. It is index reversible, meaning that due to the full utilization, the full data could be restored using the hash table, the index table. It is partially locality sensitive, and additional computation is needed to establish the neighborhood between cells. And memory complexity or consumption is exponential in dimensionality of data. So there are applications of this approach. One of them is in computational geometry on pixel grids. Do I still have time? Okay, so I just show you that compared to all the methods which has been discussed before, this uniform indexing method is doing very well at all the values of this T parameter. The conclusions. Grid-based approaches to indexing on discrete point sets on a regular integer grid has been the subject of this research. Uniform and non-uniform modifications have been considered and implemented in this research. The key features, which already have been mentioned, are collision resistance, uniform distribution of indices, index reversibility, lowest execution time among the competitors, and implementation simplicity. A disadvantage here is the exponential memory complexity, like for locality sensitive hashing. And a combined indexing approach was proposed to decrease the memory needs to linear complexity, which goes slightly beyond my time slot here in this presentation. Experiments confirmed that the time efficacy is quite high of this regular indexing approach, both for regular grids and for adaptive grid, which demonstrated the very same results. Applications of the approach were demonstrated. Just pictures, sorry for the lack of time. And this is it. We would like to thank you all, and we will be happy to have your questions. Andrii, please show up.
Good day, dear colleagues. Do you hear
Any
me?
questions from the audience? Yes, we have Andrii online.
Do you hear me?
Yes, we can hear you well, but the sound is a little bit low. Can you turn the volume?
Something with my
Just
microphone.
just a second. We'll try it on our side. Is it maxed out? Can you speak up, please?
Yes, what the situation is now?
It's a little bit silent. Can you try speaking louder?
Oh, okay, I try.
Okay.
So, good day, dear colleagues. First of all, many thanks to Vadim for this great presentation. Because you have made a super report without a background in this field. So I'm very appreciate and I'm glad to answer your questions.
Okay. Do we have any questions in the audience? Yeah. Okay. The audience is thinking, Andrii, what would be the next step in your research?
Now I'm working on the publication of the implementation on a GitHub. But the next step is to generalize this approach to use it for multidimensional spaces, for example, and especially I'm interested in making an approach for a computation on devices with small efficiency, small computation power, like IoT devices, like edge devices, small devices, in other words. Thank you
Yes,
for your question.
that makes a lot of sense. Do we have other questions from the audience? No? Okay, let's thank Andrii for the presentation again.
Thank you. Thank you, Vadim.
Thank you, Andrii. And our next speaker, the last one in the session, will be Alexander Nemish. And the talk is called Merging Logic and the Coinductive Selection Monad, Mixing Machine Learning into Logical Search.
Bonjour, messieurs, dames. Дуже радий вас тут бачити всіх. Гарне місце. I'm Alexander Nemish. I'm going to present a paper by Ruslan Shevchenko, who is on the Zoom call, and he'll help me answer your questions after the talk. I'm presenting the paper by these guys, and we're going to mix machine learning into logical search. So today we're living in these two separate worlds, one with declarative programming, when we operate on high level abstractions using immutable data, domain-specific languages, etc. And we have this machine learning world where everything is numbers, mutable data, and yeah, separate worlds. And we'll try to bridge those somehow. We'll talk about monads, logic monad, and their extensions and show some practical applications of this approach. So in a nutshell, categorically, monads are monoids in category of end-effectors, obviously. From programming standpoint, it's essentially a thing that implements this interface where we can wrap a value A into a monad, and we have to abide some identity and associativity laws. But essentially, it's a way to work with computations as values. So a simple monad would be an option monad where we have either a value, some value A, or absence of value, none. So we can define a monad interface for this data type where we can wrap a value into a sum, and we can flat map it. This way we can define a safe divide. For example, when we can produce a result only in case of y not being 0. And this is a monadic like style of defining this application. And using the CPS monad, it's a library written by Ruslan, we can use a direct style syntax essentially to define the same idea. Same thing, just different syntax. Other examples of monads are try, which allows us to either have a successful computation or a failure with some exception, or identity monad that basically does nothing. So there is another kind of monad invented by, I believe, like Kiselev in 2005 called logic monad. And it allows us to have computations as monads. So we have a logical computation which could be empty. That's the end of a computation. And we can combine those computations, where so it's an absence of result. And the M plus is essentially we explore all the computations from A and then lazily later from B. And this interface allows us to observe intermediate results of the computation using this F split. Yeah, so we can like extract a result of a computation, which will be option. So it's either a result or the computation has ended. And it can be a successful computation or error, and this is a continuation. So like an example, we can define a guard function that is successful for true predicate or ends the computation otherwise. And we can define a algorithm for finding prime numbers in this very high level and abstract way. So let's bring the machine learning into this. So in machine learning, everything is numbers essentially, or scores, and every decision is based on this scoring as a result of some scoring function. So let's integrate this scoring into the logical search. So we extend our logic monad into the scored logic monad when we can associate a score with every branch of the logical computation. So and then we can try to select the computation based on this scoring. Right? Yeah. So yeah, we associate score, and for every branch we can select using this fsplit methods from before. So we have a combinatorial search problem. We have this scoring thing, and we can attach a machine learning model and try to teach this model to give the best branch to get the best result for us for our scoring algorithm or whatever. So this is essentially can be used for the reinforcement learning, because in reinforcement learning we have an agent that performs some actions, and using it observes the state, performs some actions, and get some results in form of scores again. Like in a game, it's a agent, it plays a game, actions are game actions, scores are, well, game scores. So let's express this with Scala. We have an environment with some state. We can apply some action to this state, and this is our monad with all the possible actions that can be performed. And our agent would choose an action to perform and actually has a method to perform it. And we can learn in this environment and then like based on this learning to exploit the environment. So this way we can train a model that produces actions, and these actions take effect in this environment, in our reinforcement learning environment. Then we get another scoring from the environment, and we can put all this data for the learning model as well. So we can select the best actions in this environment. Like it's a work in progress, but with Ruslan working in this on this project called Scalus. Scalus is an application development platform for Cardano blockchain, and it is a it allows us to compile a subset of Scala programming language into a form of lambda calculus that is executed on the Cardano blockchain as a smart contracts. This allows us to write all the application in a single language, including smart contracts and backend logic, whatever. And we can reuse the code, we can reuse all the infrastructure, testing libraries, everything. And we can use debuggers, which is quite unique in this field. So like as an example, we can have a very simple Scala function. We just say compile it please to lambda calculus, and then we can use this function as a validator for Cardano blockchain. So this lambda calculus that is run, it's an extension of lambda calculus called UPLC, untyped Pluto score. We use CK machine, common way to evaluate lambda calculus, and this language is Turing complete. That means that we have a halting problem on the blockchain. And the usual way to handle this is to compute some sort of a guess. On Ethereum, it's a guess. On Cardano, it's called execution budget when we measure computation steps and memory used by the computation. And of course, size of script. And one interesting problem we have is that during compilation of data types and representing these data types on chain, we have at least 4 ways to represent it. On Cardano, we have this data type, which is sort of a JSON thing, where you can have a constructor 0, constructor 1, a list of arguments like bidder. It's a byte string of bytes essentially, and numbers. So you can represent this data type like this in data, or you can represent it using special UPLC terms. They have like conster in case. Or we can use a well-known lambda calculus technique called Scott encoding, where we use closures to store data. And these four representations have different, essentially scoring, they have different budgets. And these are dependent on other things. They dependent all on the actual data that is passed to this validator. So the idea is to use this, to choose the actual representation of data, like the default and in each variable, based on the test data. And we can use these reinforcement learning techniques to choose which representation is best. So the idea, we have this code when we use our intermediate representations, Scala's intermediate representation, to lower this into UPLC. And we need to choose the representation based on the type of the data and the inputs. And the beauty of this approach is that essentially we can put this, we can put this computation into this scored logic monad and just wrap it with verify and reflect and use all this framework to compute, to score each representation with the actual budgets that's going to be based on our test data. And we can choose for each instance of a variable in a program the best, the cheapest representation. Yeah, so that's essentially our approach to mixing logical search with machine learning with some real examples. This is work in progress though, but we are working like these weeks on that. And me and Ruslan, he's on the call, will help you with your questions if you have any. Thank you.
Ruslan, would you like to add anything to the presentation?
No, I think it's, I can say thanks because it was better than my usual approach to present.
Okay, thank you. Do we have any questions in the audience? Yes, thank you so much.
Thank you very much. I would like to ask you, you mean in this demonstration functional programming with machine learning infrastructure. May you say a few words or maybe more details about this infrastructure? And was it some, maybe we know that these machine learning components are in AV, as for example, in Azure, in other platforms, or it was some special infrastructure. What maybe components were used for this machine learning, where to embed these approaches and algorithms which you presented? Thank you.
Thanks. One of the beauty of functional things, it is abstractions between that you can abstract out algorithms and implementations. So if we have local infrastructure, no, one case, when we have all local, then we have something like Java deep learning library, GDAL, which use local GPU for learning. It is one thing. Second things, when we have, for example, compiler, it is not very good example. Better example may be such system which like SaaS, when users doing something, then we have many users. Then it is very it is not cheap to have GPUs on the user side. So infrastructure is just pass data to the queue, and then we have some server on the queue which process. And the beauty is that from the point of the person who write the logical part of code, it does not know this. It's not difference. He just know monad, and it's work. So, but for now, in library which published, we all examples are with GDL, not just because of its small.
Thank
for
you.
local part.
Do you want to follow up? Yep.
Yes, I see that there are different options, and approach is more general, and it is possible to apply in different platforms, not only on this. Thank you. It's interesting.
Okay. Thank you so much. Do we have any other questions in the audience? Okay. I was going to ask about the GitHub repository. Is it work in progress, or do you encourage people to start using it?
No,
It's work in progress, but it is on GitHub, I believe. Yeah.
No, you can see, but not used in production yet.
Okay, not yet.
I really hope
No,
we
you
will
can
quite
experiment.
soon.
You can run some experimental stuff, yes, but usually something is good when it have year or two, when it exists a few months or a few days, then it's very new.
Yeah, how many issues do you already have on this GitHub?
0, because we opened it yesterday.
Okay,
No, of
okay,
course,
great.
we have
So,
internal issues, but actually GitHub we opened yesterday, especially for this conference.
oh, okay, I see. Okay, great. So we encourage everyone to have a look and start creating issues so that the solution can get developed and bulletproof. All right, if we don't have any more questions in the audience, thank you so much again to Alexander and Ruslan.
Thank you.